previous video called Data Analysis Networks in DIN, we explored the idea of representing a statistical analysis graphically as a directed network. Each node in the network is a step in the analysis, and each arc a logical connection between steps. This kind of network representation has many advantages. First, it provides a more faithful record of the typically nonlinear history of a data analysis. Second, networks are easily displayed on a high-resolution monitor and can be interacted with using a pointing device like a mouse. Software developed on this model provides powerful tools for carrying out and managing a statistical analysis. Third, and perhaps most importantly, the network representation and its interactive display encourage the statistician to visualize the analysis as an entity itself. Viewed at this level, over time and possibly over many different analyses, patterns of analysis steps will emerge. Minimally, these will be collections of only a few steps each, but potentially could involve many sub-analyses. In any case, it would be valuable to capture any patterns identified so that they can be used as building blocks in future analyses. In the present video, we propose to have the user capture these patterns graphically. By pointing at a pattern in an existing analysis, a program is created which will produce that pattern in new analyses. Since no code is actually written or even seen by the user, we call this technique graphical programming. In this section, we review properties of analysis maps. Analysis maps are the windows where we actually view the network representing the statistical analysis. Here we have a statistical analysis on some data, some demographic data, on 49 different countries. In this particular network, there are only 6 nodes, 4 at the top and 2 at the bottom. The 4 at the top represent data from the countries, the actual names of the countries, the gross national product per capita, the infant deaths per 1,000 live births, and the number of people per position in that country. As we can see, there are arcs connecting some of these nodes. These are logical links indicating that from these data items, we went down it and did another step in the analysis. These small boxes here actually represent sub-analyses. And as you can see, when I click on them with the mouse, they highlight, and I can get a menu from the left button of the mouse which will extract information from these individual nodes. The menu is I can name the node, I can edit some notes on it which may contain more information about what this node is. I can zoom in on and inspect the internal details of that node. This is available on each node, and if I zoom in on this small box, we see that it is a sub-analysis. Zooming in will produce another analysis map much like the one we're just doing. So let's zoom in and an analysis map will pop up on top of this one. Here we go. So here's an analysis map that represents a sub-analysis of the larger analysis. And you can see that this one's far more complex. In the top left corner contains a couple of box plots, one here and one here. Again, I could zoom in on these and see what they contained. In the bottom left corner is another sub-analysis. This analysis is within this particular sub-analysis, which is contained in the larger analysis. Analysis maps can be nested to arbitrary depths. In that way, we can confine our attention to any particular part of the analysis that we're interested in. Go to the right here, we see that there are a few more nodes, a bivariate regression, a scatter plot from the bivariate regression, also a least squares fit from that bivariate regression. These again represent steps in the analysis, and from the least squares fit we can see that there were a variety of residual plots done. Residual versus fit, a histogram, and a quantile plot. An interesting property of these nodes is that if we do a middle button selection, a menu pops up that allows us to take new steps from that node in the analysis. If I look at class-specific methods from a bivariate least squares, for example, you can see that from here I can extract a variety of residual plots, residuals versus x, residual versus index, etc. Other interesting features, I can extract data items from this particular fit. And from a least squares fit, we see that we have available residuals, fitted values, the estimate of sigma squared, the intercept estimate, etc., the r-squared degrees of freedom. So an important part of an analysis map is that we represent each step in the analysis as a node in the network. Logical links between the nodes are shown as arcs. We can access information on each of the nodes, and we can ask that new actions be taken from each node. In this way, we can continue the analysis from any particular node in the map, sort of emphasizing the nonlinear structure of a statistical data analysis. In this section, we very briefly go over the elements of a statistical toolbox. Each node in a statistical analysis map is an instance of a class. These classes we consider to be tools, the kinds of things that we can use in a statistical analysis. They're kept in something called a toolbox. If we expand this toolbox icon here, we see some of the kinds of statistical analysis nodes that we could create. Some of these we saw in the previous analysis map, like bivariate regression or bivariate least squares. Statistical toolboxes are very much like analysis maps in the sense that they're meant to be used and manipulated by the user. And like analysis maps, toolboxes can contain sub-toolboxes. Here in this particular toolbox we have 3. Each is mouse sensitive. If we zoom in on this particular toolbox, for example, we get a sub-toolbox, this one containing all of the graphics that you could use in a kind of analysis. In summary then, the toolboxes are networks to be used by the user to contain the tools that can be used to construct new analyses. Here we have the demographic analysis that we considered earlier at the highest level of organization. Last time we zoomed in on the detail of this sub-analysis. This time I'd like us to consider the other sub-analysis, looking at the relationship between infant deaths and the number of inhabitants per position in each country. So if I zoom in on this, I get the sub-analysis in its own window. And we see that this analysis map resembles the previous sub-analysis that we considered in many ways. In particular, there are 2 box plots that are in common. Then there's some transformation of the original data taken from each box plot. Then there's a bivariate regression analysis in which the data were considered graphically and fitted with a least square straight line, and 3 residual plots were considered. The analysis is in fact virtually identical to the previous, with one exception. The exception is that no further analysis has been done on the transformed data. What we would like to do is perform the same kind of analysis that we've done here and in the previous sub-analysis on this new transformed data. What we have in fact then is a pattern in our analysis. What we have are a couple of box plots and a bivariate regression analysis. We'd like to capture this pattern in a generic kind of tool. To do so, what we do is go to the menu items on the analysis map itself. Amongst these menu items is the possibility of creating a new analysis path. If I select this, I get a little window where the analysis path is going to be constructed. In the prompt window, we see that we're prompted for members of this analysis path. Here what we want are examples of what the analysis path should look like, what nodes it should contain. So I'm going to start filling this up with the nodes that I would like, namely box plot, the other box plot, and the bivariate regression analysis with all of its details. So I've selected all of the nodes that I'm interested in, and what the program notices is that in constructing the nodes that I've looked at, that I've selected rather, it's necessary to have something called infant depths. So what it's prompting us for is a name for this thing called infant depths, a parameter name, if you will, that it can use in the future. The infant depths, you'll recall, was the response variable in this analysis, so I'm going to name this parameter response variable. The other thing that was needed was the x variable, which here was the number of inhabitants per position, and we'll call this the explanatory variable. These variable names are chosen so that they're describing the role that was played by each of those data vectors in the original analysis map. Now then, what we have before us is the analysis path as constructed. These nodes, while they look much like the nodes of the original analysis map, they are in fact generic nodes that contain no data at all. That's why the box plots and other graphic features are not displayed. I can name this analysis path, and I'll call it something that has some meaning for me, so I'll call it a reg analysis. And if I compute this analysis map, you see that the name appears in the title bar. Now then, what I would like to do is apply this generic analysis path to a particular data set. In fact, I'd like to apply it to the transform data that we considered before. So in the menus for the analysis map, what I will do is add a new kind of analysis node. And when prompted for it, the new kind of node I would like is the analysis path that I've called reg analysis. It constructs the new node and asks me what is the parameter that is equivalent to this thing called explanatory variable. This time I'd like the explanatory variable to be the transformed population per position. So I select that from my existing analysis map, and I'm prompted for the response variable. The response variable will now be the transformed infant depths. At this point, it notices that it's possible to add some string vectors here corresponding to the observations. So I'm going to select countries from the old demographic analysis, since it's the same data set, for the labels of the string vectors. The analysis path then constructs the nodes that it needs for this particular data set. And I'm prompted to sweep out the windows for this node. Here it's the window for the box plot of the transformed population per position, and now the box plot for the transformed infant depths. It goes on to calculate the bivariate regression nodes and the bivariate least squares nodes, and afterwards the plots for the residuals. Okay, so here's the first plot that it constructs that involves both of the variables at once. It's a scatter plot where we see the data are fairly bunched up, and this scatter plot can be rescaled to spread the data out. Next plot that it produces in the analysis path is the QQ plot of the residuals from this new fit. Second plot of residuals is the histogram of the residuals from the fit. And finally, the path constructs the residuals versus fit node. So each of the plots that were considered in that path are now available to us to consider further, should we wish to. And if we notice, the analysis map now has a new node. If I recompute this thing to show the whole analysis map, I have a new node that is a sub-analysis. It comes from the transform data set, and it's sub-analysis representing that small analysis that we just applied. In this way, the analysis path that we created has created a smaller analysis, which is a larger building block than the previous, more primitive building blocks in our analysis. It's a reg analysis. If we zoom in on this, we can see the details of that particular sub-analysis. Since we've used this path in more than one place, it may be useful to keep this path for use on other data sets. To do so, I add the analysis path corresponding to this node in the toolbox. If I open my toolbox, then I can see the tools that I have, and I'd like to add a tool to this thing. So the toolbox menu, if I widen the toolbox, I say that I want to add my reg analysis as one of my new tools. And I'm offered to place it in the toolbox where it makes most sense to me. I'll just put it up near the root of my toolbox. We see that the toolbox is expanded to accommodate this new node. The new node has a different icon from the others. These other icons are sub-toolboxes. This item here is in fact an analysis path. The icon is meant to indicate that it's something that is rather complex that can be applied to new data. Now then, if we zoom in on this icon, we can see the details of that analysis path, so that what we see that is this little network here is in fact the internal structure of a new program that we can apply to new data. In this section, I'd like to demonstrate how graphical programming can be used to construct new programs that are not necessarily based on patterns you've observed, but something that you've planned in advance. We'll still need to work from an example, however. So here, my interest is in constructing an added variable plot, and I'm using the example that we had previously, the demographic data, and in particular the three variables: infant deaths, population per physician, and the gross national product per capita. What I have in this analysis map are two least squares fits. The first least squares fit is a regression of infant deaths on number of inhabitants per physician. The second is the regression of the GNP on the number of inhabitants per physician. The added variable plot then would be the plot of the residuals from this regression versus the residuals from this regression. That plot is used to see whether or not the GNP has anything to offer over and above the population per physician in fitting the infant deaths. So the first thing I need are the two residual vectors from each of these fits. Get the residual vector from this fit by simply extracting it. There it is. And now extract the residual vector from this fit. So I'll need to add a plot to these two, so I'll widen the analysis, getting a new node. Getting a scatter plot here. And the x variable will be this residual vector. The y variable, this residual vector. And I'm prompted for a string vector, which I'll choose to be countries for the particular example we're constructing. So the scatter plot is calculated, and we're prompted to sweep it out on the screen. There's the added variable plot. You can see that it's certainly nonlinear as might be expected given we needed to transform the data. I'll link it in the analysis map to the two residual vectors that it's based on. So constructing an added variable plot depends on these 5 nodes: the 2 fits, the 2 residual vectors, and the plot. So I'll create an analysis path that I can use to construct future added variable plots by selecting these 5 nodes. The population per position was the x variable that we had in common between the 2 plots, so I'm going to call that parameter the common x. Infant deaths was the response. And the GNP per capita was the new x. So there's the analysis path constructed. Let's give this analysis path a name. We'll call this the added variable plot, since that's what it produces. So there's the added variable plot as a tool to be used in other analyses. If we apply this tool now to the transformed data, as an example, I've got a new analysis map in the top here containing the transformed data, and I can widen this view, adding a new kind of analysis node. The new kind of analysis node here will be the added variable plot. The parameter equivalent to the new x variable, again, will be the transformed GNP. The response is the transformed infant deaths. And the common x is, again, the transformed number of inhabitants per position. Constructs the least squares fits for this new data set. It will soon prompt us for the labels to be used in the added variable plot. So the labels, remember we're using the same data set here, so I'm going to put in countries once again. And now we're prompted for a position for the added variable plot. And here's the added variable plot on the new transformed data. Okay, let me rescale that so we can get a better idea. There you can see that the transformed GNP does seem to have something to offer in explaining the variability in the transformed infant deaths over and above that of the number of inhabitants per position. So there we have it. All that remains now is to take our added variable plot and add it to the toolbox for future use. In summary then, we note that with graphical programming, new programs can actually be written by interacting with the graphical display. Of course, this depends on having a graphical representation of an analysis. And the results here should be applicable to other domains which can be represented as a network on the screen.